Okay, we should be good. Why do you think this happens? And it's also very weird, right? Because we're going from a positive number to a negative number.
Because the integer has fixed size. In memory, it has, I think, 32 bits. And the first bit is responsible for the sign of integer. So once it surpasses the...
Yeah, so I know that you know why. So there's a lot of things that you have hidden under the carpet there, right? Under the rug. So it's true, 32 bits. First bit denotes the sign. We have to learn about this encoding, right? So actually, C doesn't make a difference between signed integers and unsigned integers, right? And it takes advantage of an encoding called 2's complement. All right, so let me write it here, 2's complement. All right, that allows us to not make that distinction. It treats the bits as if they were numbers, irrespective of whether they're signed or not. The distinction happens when they get printed and when they get compared. All right, so we're going to learn soon about signed and unsigned numbers, right? So one thing that we learn from here is that ints can be both positive and negative, right? And when there's a number beyond which we can't exceed, and when we try to create a number that sort of exceeds that, we are coming back to negative numbers, right? So there is a cyclicity. We're going to try to discover exactly the value where this happens. So let's look at this value here, right? I'm going to copy it. Come on. So I'm going to start from here. So now, because it happens within 10,000 numbers, right? Why do you think I stepped at a step of 10,000? Why do you think I used 10,000 here? Yes, I didn't want to wait all day, right? So I have stepped with large steps so that it will finish relatively quickly, right? Because otherwise, in 1 million iterations, if my increment was 1, I would actually not hit the large number, which we'll see immediately is in the trillions, right? So this is about 2 trillion, what you see here, right? So with 1 million increments, I would only hit that 1 trillion if the step was very large. But if I start from here, I'm very close to that value. So now I can afford to step by 1, right? So if I step by 1, I'm going to find out exactly what that value is. Okay, so going here, and actually to make it nicer, we should actually break the loop here. We don't need all the other numbers. I'm just going to say break. Yeah, I mean, that has to go everywhere, sorry. N plus 1, N plus 1, okay. All right, so this is the number. Okay, what's so special about this number? I'm going to go in Python 3. What's nice about the Python numbers? We have infinite precision, right? Very good. At the expense of, as the numbers grow larger and larger, the time for each operation grows larger and larger. But it's a very nice feature. Okay. So I'm going to. So for instance, I can compute 2 to the power of 32. All right. Which is definitely larger than this guy. That's because we have infinite precision, right? So I'm going to try to understand what this number is. Okay? So I'm going to say 2 to the power of 31 minus 1, right? And I'm going to see that I have gotten exactly that number. Okay? So as we go from this number, we add 1 to this number, right? In C, we're going to go to negative numbers. Now let's try to understand why this happens. So let's try to count in base 2. Let's try to count with bits. So I'm going to put on the side. Actually, what we have here is we have the line numbers, just that they start from 1, and we would like them to start from 0. So remember to subtract 1 all the time, right? So the first binary number will be 0, right? The next one will be 1. And then we have run out of digits. So what's the next digit combination? 1, 0, very good. And then we go to 1, 1, very good. Then 1, 0, 0. Everybody understands this? 0, 1, 1, 1, 0, 1, 1, 1. Okay, so we have 8 numbers. And then what we generally like is to align the numbers. Okay? So let's say that I have a computer whose processing power, whose processing ability is only to process 3 bits at a time. Okay? So I could represent 8 different numbers. And if you look here on the side, right, we would have the numbers from 0 to 7. If we would consider that these combinations represent all positive numbers. But the world is not made of positive numbers. I want the numbers to be negative as well, right? So I have to start to come up with a convention that to make some of these numbers negative. The 2's complement, all right, is extremely nice because as far as addition and subtraction is concerned, it doesn't matter whether I'm in the unsigned natural encoding or I'm in 2's complement. That's why it is used. Okay. It also has the nice feature that all the numbers beginning with a 1 are negative. So this is like a rotational cycle. I'm just going to add some space here. So we're going to start counting from 0. Sorry, 1, 2, 3, and when we have exhausted half the codes, we're going to consider the axis, the interval of representable numbers, right, as being symmetric with respect to 0, right? So if I have 8 numbers, I will probably be able to go into the range of positive numbers until the number 3 or 4, right? Because half the interval should be positive, half the interval should be negative, right? If you look at 0, you would say that, oh, it's neither positive nor negative. So then there will be a little unbalance there, and we're going to have to decide which are the which side is going to suffer. The positive numbers are going to have your codes, or the negative numbers, right? And the convention is actually that we take away from the positive numbers. So 0, 1, 2, 3, we sort of hit the half of the codes, and we're going to circle around and start with the smallest negative number, right? Which is going to be -4, right? So -3, we circle around. Is this clear? Yes? This is what we call complements, the complement of 2. All right? So we have 2 possible encodings. The natural one, which gives us only positive numbers, and the 2's complement. Yes, please. Yes.
So it is just that we see that it should be like the whole list should be the power of 2, or
yeah, so 8 we have 8 numbers, right? So negative numbers are gonna the negative numbers are gonna start at -8 divided by 2, right? So and then you'll derive very easily the rule for the positive numbers, right? So this is going to be n, where n is the when n is the number of numbers, right? Or let's say k is the number of bits. So I'm going to say 2 to the power of k minus 1. I'm going to use Python notation here. So this is going to be the lowest negative number, right? And the highest negative number is going to be 2 to the power k minus 1 minus 1. All right, these are well-known things in binary arithmetic. Does it make sense? So now, this is how addition works. This is how addition works. Let's say I want to add 3 to 2. So I'm here, and I'm going to count 1, 2, 3. 3 plus 2 is minus 3, right? That's how it's going to work. 3 plus 1, so I'm at 3, plus 1, I go here. 3 plus 1 is minus 4. Clear? This is complement of 2. You have to think of the range. Obviously, with only 3 bits, you can't represent an infinity of numbers, right? So it's going to be a range, right? So you have to think of the range as being a circle, where the largest number and the smallest negative number are consecutive, right? Similarly, minus 4 minus 1, which normally would evaluate to minus 5, is going to be 3 in this case. Okay? So now, instead of having 3 bits, imagine you have 32. This is how many bits a C integer has. Okay? Now we're going to do a very interesting thing. We're going to say, so I'm going to go back to the original version of the program. I'm going to Control Z. And actually, I'm going to put back the break here. And I am going to say that this is an unsigned int. Unsigned integers, instead of splitting the range between negative and positive numbers, uses all the numbers as positive numbers. So it's just a matter of encoding. It's the same bits. They fit in the same amount of memory, 32 of them, just that when I print them here, they will be considered without a sign. And by the way, in order to accomplish that, I have to say that this is unsigned, and this is also unsigned. Okay, and let's see what happens now. Okay, so we still have only 32 bits. We still have a limited number, a limited range, but that range starts at 0 and ends to at. So this time we have from 0 to 2 to the power of k minus 1, right? So 3 bits means from 0 to 7. But the circle principle still applies, right? So we count from 0 to 7, and after that is 0, back to 0, right? Does that make sense? So there will be a number, right, which when we add anything to it will result in something smaller than it. And going to Python 3, since I told you already that it's 32 bits, we can find out what the number is. Right, is this value. Okay, so I can essentially, we can rediscover this value by doing what we did last time. 32 minus 1. 32 bits. Okay, there's this number. So we can do what we did last time, right? We can start from this number which we have discovered. Okay, and we put it here. And again, 1,000,000. And we only do 1 and 1 and 1 and oops, compile, run, and here as well, I forgot this one. Okay, so we found it, right? So look at what n plus 1 is. The value is 0. Is this clear? Everybody understands this? So this introduces serious limitations. And actually, this kind of limitation, you will find it in Java and a lot of other languages, right? There are very few languages which have infinite precision arithmetic. The other one is Haskell, right? So I only know Python and Haskell. And that's a very good thing, especially when you teach kids programming, when you teach beginners programming. It's a very good thing to not have to worry about this, because it can introduce very serious errors. Now, Java has done away with the shorter types. We're going to learn soon other types of integer, right, which use fewer bits. And because of that, the errors that are that come because of overflow. So this is called overflow, right? You're taking this value, it overflows, it can't fit into 32 bits, and you get what remains. They are much less frequent. In the old days, memory was very expensive. You would try to use exactly as much, the number of bits, exactly as many as you could afford for that amount of data, right? And because of that, these overflow errors were extremely common and very difficult to find. So let's look at other types of integers. So I'm gonna use a short integer. Okay, I'm going to start again from 0. All right. How many bits do you think the short integer has? A bit more than that. Has 16. All right. So let's actually here we could, because I is int, right? So here actually I can use 100,000. So if you're curious what kind of value do we have with 16 bits, let's go here and try to find that out. Right? So 2 to the power of 16 is a very puny number. Okay, very small number. So obviously, what's going to happen is that as soon as I reach 65, actually, let's not worry about the example because it takes time. As long as I'm going to reach this value minus 1 and add 1 to it, I'm going to go back to 0. So this is for an unsigned. For a signed short, which is what we would get here, for a signed short, right, we would have this as the maximum. Okay? All right. And there's another kind of int that is very short, right, which is called char. You're going to say, wait, isn't that the same thing? Yes, it is. Right? So int was so unrefined, sorry, C was so unrefined as to not recognize the difference between integers and characters. Right? At the time when it was invented, the prevailing character encoding was called ASCII. Right? The current UTF-8, which is part of Unicode, is an extension of ASCII. All right, so the ASCII codes of the olden days still can be in use, just that it's extended and can allow more a larger set of characters. But the ones that come from English that are very common, the ones that you find on the keyboard, those have the same codes, right? And you only needed 7 bits for them, right? So C, in spite of the fact that memory was so expensive, decided to be be generous there and allowed 8 bits. Why? Because it wasn't nice to use 7, right? It's nice to use a power of 2. 8 is close to, I mean, it's exactly a power of 2 and larger than 7, so it allows all the characters to fit. But characters are actually integers, all right? Don't be mistaken. So let's do an experiment and prove that. So I'm going to start with char from 32. Anyone knows why 32? And it happens to be a power of 2. That's not the reason. No? Okay, I'm going to start from 32 and then we're going to change it to start from, let's say, 0 and see what happens. Okay? So for int I equals 2, and we were saying that it's to the power, so it's 7 bits, right, to the power of 7. So I'm going to go to the power of 7. How do you think I will express to the power of 7? So the syntax in Python happens to be the same, but Python allows me to evaluate expressions directly, so let's just go there. So if I want to find out to the power of 7, of course I can use this operator. All right? But do you know another way? Which the power operator is not available in C. No. What's that? Bit operations. What bit operation will you use? Dash dash? Okay, so you would use this, right? So what does this mean? Shift to the left, okay? So let's try to understand what these shifts mean. So let's say I have a number, a binary number. Let's say I have, I'm going to take 4 bits, 0, 0, 1, 1. And I only have 4 bits. Previously we worked with 3. Let's say we only have 4 bits. I'm going to shift these bits to the left by 1. So by the way, 0, 0, 1, 1, what decimal number is it? 3, right? So I'm going to shift it to the left. So I'm going to put a 0 here and delete a 0 from the front. What number do I get now? Six. Very good. Right? How do you compute? Right? So this is on the 4th position. So you multiply with 2 to the power of 3, right? This is on the 3rd position, so you multiply it to 2 to the power of 2. This is on the 2nd position, so you multiply it to the power of 1. This is on the 0th position, right, on the 1st position, so you multiply it to 2 to the power of 0, right? So you should compute 0 times 2 to the power of 3 plus, let's not leave the spaces because it creates more confusion, I think, plus 1 times 2 to the power of 2 plus, is this clear? You would do the same in base 10, right? 1 times 2 to the power of 1 plus 0 times 2 to the power of 0, right? That's the formula. So if you compute this, you get 6. So from 3 to 6, right? Shifting by 1 and filling the remaining positions with zeros leads to multiplication by 2. It's the same thing, right? So if I'm going to shift by 7 bits, it's multiplication to 2 by 2 to the power of 7, right? So if I take 1 and shift it by 7 bits, I'm going to get the value of 2 to the power of 7, right? So I'm going to go up to that value, right? But I was saying it's 7 bits, right? So actually 128 is exactly higher than the largest value for 7 bits, considering the 7 bits as a unsigned number. So this should be 127. So I'm going to say here I less than 127. All right, and I'm going to continue incrementing n by 1, but actually this 127, I'm going to subtract the 32 that I had there, because we're not printing 127 numbers, we're starting from 32, and we want to finish at 37. So I don't want an if, I'm just going to print, and I'm going to print n equals percent C. I don't care about n plus 1. Guess what? This is the character code. So let's run this program and see what comes up. And we shouldn't call it maxint anymore. There shouldn't be a short here. Okay, so what do you see we're printing? Printing characters, right? But n is essentially starting with an integer value, right? So the first value is going to be 32. And what do you see here? The space, right? That's why I started with 32. What do you think is below 32? Very good, non-printable character. So it's stuff that will mess up our screen. Okay? Before I go there, and we're going to mess up the screen because we're learning, let me print this as a D here. And we're going to say, can we do that? And why not? Might get a warning. We don't even get a warning, right? So you see the integers, right? We're starting at 32, and we're ending at 126. So we probably should say less than or equal here. Okay? So let's print both. Let's print both the percent %C and the percent %D. Okay? So what happens now is that you're seeing very clearly that characters are in fact integers. And here I should have n twice. We want to print it once as a character and a second time as a integer. Okay? So we have the correspondence, right? 32 is the space, 33 is the exclamation mark, right quotes, and so on, right? And you see that n starts at, number starts at 48. So you'll see this kind of things very often in programs. And then capital A is 65, and I think small a is 96 or 97. Okay. Now, do I have to remember these codes? You might think that I might need to remember. Actually, no. All right. So there is a way to represent characters as characters, though they are still numbers. All right. I can write this. So there's a space here, and within single quotes, that is a character, right? So that is another way of writing 32, as a matter of fact, right? That thing, right? This expression and the number 32 are exactly one and the same thing. So if I write again, I'm just going to get the same thing. There's no difference, right? Let's say I just want to print the small letters. So I'm going to start from A, okay, and I am going to, there's 26 of them, right? So 26, and what's going to be less than, and let's run this, and we only have the small letters, right? We know there's 26 of them, We know the first one is A. I don't care what the code of A is. It happens to be 97, but I don't have to know that by heart, right? The code will help me. Okay? Now, let's say I want to print both the small and the capital letters. What am I going to do? So instead of this %d here, I would like to print the small letters and the capital letters. What do I do? So you're going to say, oh, let me go here and remember that, you know, this is 65 and then this one is 97. So do 97 minus 65, right? And I don't even know what that is. I'm not going to bother to compute, and then subtract the number from here, right? But instead of doing that, what I could do is say small a minus capital A, right? And subtract this value. Right, that'll be good enough. Yeah? Cost what? Yes, I told you it's an integer. This is just another way of saying 97. It's not a character, it's an integer, right? It's an integer that has only 8 bits, remember. Okay. So now we have all the characters, both small and capitals, right? Now, one very small, what I promised previously was, let's see what happens. Let's mess up the script a little bit. So instead of starting at A, let me start at 0 here. All right? And let's do 32 here, because we are saying that there's 32 non-printable characters. Right? So actually the Mac OS is kind of nice and doesn't let us mess up the screen too badly. Okay? What happens? These are in general controlled characters. All right? So for instance, one of the characters is, one thing here that would be nice to do, just 1 minute and I'm going to finish, is let's also put the value. So you will notice a few things. So I'm going to put another n here. So you see now n is printed as integer and as character with its capitalized value. Actually, we don't need a capitalized value here because the capitalized value of a non-printable character doesn't mean anything. So let's do this. But let's try to infer some stuff. Right, so you see when you have n equals 10, right, there's this line in between. And there are several places where that happens. Let's do another thing for more edification, right? So I'm going to say printf here for the on the last line, and I'm going to say \n equals %d \n \n. This will be very confusing, probably. Okay, so let's run this again. And this is what we see, right? So we were saying that whatever we put in single braces is an integer, right? The value of that integer is 10. Right? What does \n do? Goes to the next line. What happened here when we try to print it? Because you see, we actually print the character. We print its numeric value, and then we try to print the character itself. We try to let the computer interpret it as the control character it is. And what does the control character do? Puts an empty line, goes to the next line, right? So that's what happened here. All right, so these characters have the ability to control the formatting of your output. One of them is the tab. So let's see if here we actually can see the tab. The tab should be, I think, 8. So if I try to, so you see, if I try to select, okay, I have the option of selecting one space or the entire line. If I go to this line, I have the option of, then say maybe 9. 9 is the tab. Okay, you see? So there's a tab here. So the tab represents a number, an alignment character, right? Which aligns on 8 characters. So from the beginning of the line up to here, there should be 8 characters, right? It sends the cursor to the next block of 8 characters. So that tab is there as well, right? So these are the control characters. I think this is enough for today. We're going to go into talking more about bits and the hexadecimal notation next time. This is the second week, so at the end of this week, there's going to be also the first assignment coming up. Check the canvas. There is a way for us to communicate over there. I would like to know whether that works. So I haven't used it, so try to post your questions if you have any. If not, try to come up with some questions or just say test. And I'll be checking to see whether it works. I should be posting something as well. Okay, thanks for coming.